So we're looking at your Canvas right now. You'll notice at the top I say Teams Access. Go to Waffle in Window 365 and put in the code T34XSBO. So I'm going to just walk you through this so you know what this is. Okay, so when you have time you can do it. Once you go to Office, you should look like something like this. The waffle is this thing in the corner. Okay, it looks like a waffle. You click on it, and you're looking for Teams. If you click on Teams, it'll come up with a purple background with a T and load. When you get in here, on the side, there's a button on the side, third one down, it says Teams. You're going to click it again. When you do, it'll ask for a code. The code that you want is this one right here. Okay, you put that code in, and then you have access to this. The chapter videos will be in here underneath Class Notebook. Excuse me. So you can just click on this and it will go through Teams. It does not go through YouTube, so you can watch it at school. Okay, you can watch it anywhere. But it doesn't go through YouTube. So this is another way to do that. At home, if we go back to home, come on. I can actually see everything that you've got. There's some collaboration space in here that you can actually go into and talk to different kids and things. But if I go, there we go, home, conversation. So if I go to conversation here, you can talk to other kids that have signed up for teams. So in CE, we'll all be a team. 5th period, 7th period, and 8th period, all be a team. Please don't use this during class, okay, because it's like an instant message. But you can use it after class if you're out and you said, you know, hey, what did you guys get for this part? Or I'm not understanding the lab part, whatever. Does anybody get that? They can answer you here. So you don't have to have everybody's text message ability in the class, but it's right here. Okay? If there's any files that I want to save and give up to you, they'll be here. I also put the suspension day 1 there, so there's a video there. But then I decided that I'd put them in Class Notebook, but I haven't moved that other one over. Also at the top here, you'll notice there's the heating curve and the solution of mixtures. These are Nearpods. So this actually gives you a bigger screen for the Nearpod. You know how in Canvas it's just really small. And this one it takes almost all of the area. In fact, I'll just show you real quick. It takes that whole big area that you can actually see and go through. Okay? As I get more stuff, I'll add more stuff for you here. But again, I will keep this up so you can go back and look at it. Any questions with this? Okay, so there's another thing we need to talk about before we get right into notes. And that is, as I was putting, there's some parents that have asked me to put snippets or snapshots of your grade onto the DSD system. It's not going to be upgraded or updated more than 4 times. I'll do sometime before midterm, sometime after midterm, and final. Your grade on Canvas is always up to date as it can get. Okay? Now here's the problem. Weber State syllabus states that you have to have 80% in lab in order to pass the class at all. A lot of you do not have that. Okay? So I have opened all the labs until May 17th. That doesn't mean that you can just wait till then to get them in. You've got to get what we do this term in this term. But if you don't get it in, you can turn it in next term, but I'm not going back and changing this grade. Does that make sense? I did offer that if you work really, really, really hard and you get your grade up at end of 4th term, and that's the grade that goes to Weber, and it's higher than any of the others, I will go back and change it to that all the way through. Okay? But you got to come and talk to me about it, because I won't just do it. Okay? So I have opened that up. I've opened the Learn Smarts. I've opened the homework, all of them, till May 17th. Okay? So, if you are one of those people that has a bunch of zeros in assignments or homework or Learn Smarts or labs, you have a chance to get your butt in gear and get some of that done. 20% is lab, 20% is homework and assignments. That's 40% off the top. That means if you got 100% on all your tests, you'd still get a D-. Barely. Okay, so please get that stuff in. I'm doing all I can to do to help you get passing and get the best grade you can in here. But you got to put forth the effort. I cannot do it for you. Okay? Any questions with that? Yes, sir.
Is there a way that we can see what our
Yeah, you should be able to bring... it is, so if you go into your grades, scroll all the way down, and it'll give you a percentage. Okay? If you want to go over any of that with me, we can. It has to be over 80%, and they can see it. I can see it right on my screen and say, oh, you're low, you're below that, you're below that, you're below that. I can't pass you. Okay? I don't want to get down to fourth term, end of the term, and say, you know, you had a B in with all of it mixed together, but your lab is below 80%. I can't pass you. Okay? So I'm giving you everything I can possibly give you. Got to do the labs. Okay? There are 13 required labs, and we've got almost all of them done. They're in the yellow up there, and the one we're doing right now I have not yellowed out. So they're on the corner of the counter up there. We have a couple more labs after this one. Yeah, I think we've got 4 or 3. We have 1, 2, 3, 4 more after this one. Okay? We'll do little activity labs, but they're not required, but they'll help you. Okay? Any other questions real quick before we go on? All right, let's go. So today we are doing parts A, B, and C. Alex, put that away, please. Get out your notes. Thank you. We are talking about dissolution, unsaturated, saturated, supersaturated, ppH, ppm, ppb, pptr, ppth, a lot of different things like that. Next time, you need to be prepared to finish part C and do part D in lab. Those are really important that you're ready to do that. If you get done with this in lab, and a couple of groups have, you can come back in here, you can work on LearnSmarts, you can work on homework, you can work on finishing that part of the lab write-up. Okay? There's a lot of things you can do, but you got to move. So, going forward, first thing we need to talk about is the difference between solubility and dissolution. Solubility is how much can I dissolve? Doesn't matter how long it takes, but how much could dissolve in this much water. That is solubility. Dissolution is how do I make it dissolve? Is it going to dissolve faster if I do this? So I call this my Kool-Aid rules. This is how I remember it. If I make Kool-Aid with a big solid rock of sugar and really ice cold water and don't stir it, how long is it going to take to get Kool-Aid? Really, really long time. But if I crush that up till it's powdered sugar and I heat up the water and I stir it, how long is it going to take me to make Kool-Aid? Not very long. However, it's going to be hot and that's going to be pretty nasty. But I'll make the solution quicker. Okay? My mom used to give me warm Kool-Aid and warm Jell-O when we were sick. It was the form of, what do you call it? Like Gatorade, when they didn't have Gatorade. Yeah.
Where are these notes?
Back there. And you'll need to grab the lab too. I'm not sure. It was right after the heat, the solubility curve. So we're going here now. So if we have, for most ionic and molecular solids, solubility generally increases. So we had that chart, right? And all of them increased except for one. What was different about that one? So what was different about that one that went down? What type of solvation did it have? Exothermic, right, because as I put heat in, it got less soluble. So the ones that have endothermic solvation get more dissolved as we get hotter, right? But if it has exothermic solvation, then less gets dissolved as you go with time. All right, so if I heat it up and I put more solution in, because it's an endothermic solvation, put more solute in, and then I slowly let it cool. I get to a cooler temperature and it stays in solution. This is how we make candies. So how we make fudge, how we make all these different things, is we heat something up, put a lot of sugar in it, and cool it down slowly. Has anybody had a bad batch of fudge that has like crystals in it, and you go to bite it and it's like, oh, this doesn't taste right? That's because they cooled it too quickly. And because they cooled it too quickly, they got sugar crystals that fell out of solution. So if we cool it very slowly, we get what's called a supersaturated solution. We use it a lot in candy making and sugars and lollipops and things like that. Up here I've got homemade rock candy. If I put on that stick, if I make a supersaturated solution and then on that stick I just put a few crystals of sugar and put it down in a supersaturated solution, the sugar from the solution will start to crystallize on what we call that seed crystal. And we get those rock candy suckers. Okay? So, just remember, supersaturated, it contains more than it should at that temperature. So, as we heated a liquid, for the most part, if it was endothermic solvation, we got more in. Well, if we heat a substance that has a gas dissolved in it, we have less that will be dissolved in. So as the summer months get hotter, the lakes hold less oxygen for the fish. That's why they stay up towards the top, because that's where the oxygen's going to go out. In the winter, you'll find them down at the bottom because the coldness of the lake forces the oxygen down in, so they can go down to the bottom of the lake and be just fine. If you look at the pop here, if you have a cold pop that you had in the fridge and one that was just out at room temperature and you pour it in, that's what's going to happen. You'll see it's called effervescence when the bubbles come out. The one on the right has a lot more effervescence because a lot of the carbonation is coming out of it. Carbonation is caused by carbonic acid being in solution, okay? And as the carbon dioxide comes off, it leaves water behind. And so when we go drink our pop after it's been open for a while, we say, oh, this has gone flat, it doesn't taste right. That's because the water left behind is diluting the syrup that made the pop. And so it doesn't taste the same, it's very dilute. Okay? All right, going forward. This is Henry's law. Henry's law has to do with gases in liquids. If I apply a pressure to a gas, above a gas in a liquid, then the gas is going to stay in the liquid. And this is what they do with pop. This is sort of like Gay-Lussac's law, but instead of on the bottom where temperature was, we put solubility. So it's pressure divided by solubility equals a new pressure divided by the new solubility. I did not put that law up there, but because she doesn't seem to have you want to know it, but as far as you do need to know the law, but you don't need to know the actual law. Does that make sense? Okay, so if I release that pressure above the pop by opening the can or opening the pop bottle, then the gas is able to release because that pressure is no longer holding that gas into the liquid. So the higher pressure, the more gas molecules dissolve in the liquid. Lower pressure, when I release it, they go out. Yep. Mm-hmm.
Okay, thank you.
Uh-huh. So the next thing that we need to worry about is percentage problems. Most of you know how to do percentage problems. You know how to find your percent on a test, right? What I got divided by what the total of the score I could have got, times it by 100. In science, we don't call this percent. We call it pph, parts per 100. Okay, but it's the same thing that you have done forever to find your percent on the test. Okay, so we're going to use that because in medical and in science we use pph, not percent. Okay, now we use ppm a lot. It's the same as percent except we times by 1,000,000 instead of 100. So ppm is parts per million. You'll notice on the side there it has differing concentrations of a substance. 1 part per million, you can sort of see it, a light yellow, but by the time you get to 10,000 parts per million, it is almost a dark red. Okay? So as we look at different things with parts per million, oh, I just love this. We can get, they use parts per million a lot with air quality and water quality. Because we don't want very much lead in our water. We don't want, contaminations like that. The same thing is on this next page, but it breaks it down a little bit more into other things that you might need to know. So part per 100 is 1/100th. Part per 1,000, 1/1,000. Part per million. So as you look at it, it sort of gives you a description above. Part per 100 is like 1 drop in half a cup of water. So that's a lot of the half a cup, really, compared to these others. 1/1000th, or ppth, is 1 drop in a quart of water. So a quart is 2 pints, and each pint is a cup, so that's about 4 cups of water. A drop in 2 tubs of water is about part per million. One drop in an Olympic-sized swimming pool is about 1 part per billion, ppb. And then when we get up to a big lake, 1 drop in a big lake is about 1 part per trillion. So that's a lot less. You can get this on the internet and actually go in and click on these each different ones, and it goes into a little bit more visual thing. But we're going to look at another little thing here. I'm going to have this play for you so you can sort of see what's going on, give you a more idea of what
is a unit of measurement. Parts per million counts the number of units of one substance per 1 million units of another. It can measure concentrations when a small amount makes a big difference. For example, a concentration of just 35 ppm of carbon monoxide in the air is poisonous to us. We encounter measurements like this pretty often, but because it's hard to conceptualize really large numbers, it's difficult to wrap our brain around what 1 part per million really means. So here are 9 helpful ways to visualize it. If you had 11,363 pianos worth of piano keys, one of those keys would be about 1 part per million. So would a single granule of sugar among 273 sugar cubes. 1 second in 11.5 days. Or 4 dots in the painting A Sunday Afternoon on the Island of Le Grand Jatte. Your bathtub's capacity is about 60 gallons. So 7 drops of ink would be 1 part per million. The English version of the Harry Potter series has 1,084,170 words, which makes hippogriff on page 221 of The Prisoner of Azkaban a little less than 1 part per million. A million kernels of corn is about 1,250 ears, so 1 kernel in that truckload would be 1 part per million. There are 10 million bricks in the Empire State Building, so 1 part per million would be a pile of just 10. And finally, 100 people worked together to animate this video. Collectively, they have about 10 million hairs on their heads. Pluck 10 of those hairs, and you have 1 in a million.
I love that one. It's so cute. Poor guy. He didn't have any hair left to pick. Okay, so let's go on to the next one. This one is where we learn a lot. These are not in order, they're in notes, so be careful. This is where we use the medical version of it. So weight percent, weight to weight, volume percent, volume to volume, and weight to volume percent, which is grams per milliliter, basically. This comes in if you've worked at all in the medical field, they have saline solutions that come, usually with volume or weight to volume percent on it. Sometimes they use volume to volume because they're diluting from a different saline solution. Seldom do they use weight to weight when they're using that because they've got a volume that they know they're going to be using. So we got these down. They do the parentheses whenever they do a percent composition like this. They do always end with what's in the parentheses up there, so you know how they did it. Okay, and they know what's going on. We're going to do some example problems with each of these. We ready to roll? Okay. So weight to volume is what we're going to do first. So that's this one. So if you had an example of vinegar containing 5 grams of acetic acid in 100 milliliters of solution, so what would the weight to volume concentration be? Well, you'd put the 100 right here and the 5 right here, and when you did it, the 100s would cancel and you'd end up with 5%, right? And that's how we would write it, is 5% parentheses weight divided by volume, close parentheses, acetic acid. Pretty easy, right?
5% WOD.
Acetic acid. That's what vinegar is, it's acetic acid. Yeah, just calculating percent, right? So let's go on the next one. So if we had 70 milliliters of 2-propanol, if you've ever been put to sleep, they put you to sleep with 2-propanol. That's that white stuff in the syringe if you're doing a short surgery. In 100 milliliters of solution. Again, if it's in 100 milliliters of solution, very easy, straightforward. Volume to volume, you get your percent. Okay, going forward. Here's an example. We use a saline solution. Again, take everything that you know and take it out. So we've got 0.92% weight to volume. We're using 250 milliliters. How much sodium chloride do I need to weigh out to go with that 250 milliliters? So, again, I like to do it just simple. They'll have you do some stuff on the other page. But we know, right, that we have some amount that's going to be divided by 250 milliliters. We're going to times it by 100, and it's going to end up with 0.92%, right? So I set it up like a math problem right up front. And then I solve for x. It's not all that difficult, right? We're going to times both sides by 250 milliliters. Milliliters will go out. We'll divide both sides by 100. And I'll get my answer. And it will be in grams, because this is actually a percent where it's, since it's weight per volume, grams per milliliter. So the milliliters will cancel and leave me with grams. So what do we get? 2.3 grams is what I heard. Okay, let's see if we were right. So going on this other side, they say, okay, you can choose this or this, and then you're going to do this. And I'm like, okay, I'm done. I just like to set it up and go. Because they didn't tell me how here, what they were doing. They just said, this is what we have. It's like, I like this way where I know what I'm doing. But your choice. Okay, questions? Okay, let's do another one. We've got 3 of them. I'm going to have you do them now. You do them. Okay? And this one right here should be, the unit on this one should be grams per milliliter. Has anybody got the first one done? What is it? Is that what you guys got? Do I have a second on it? I hear some strange faces. Okay, what'd you get? 5.3. Do I have a second on that one? Okay, so we took 5.3 grams divided by 100 times by 100 equals... Okay, what about B? Do we have an answer for B? 1.35%. Do I have a second? Okay, and we should probably put after this weight to weight, and then sugar, and weight to weight, NaCl would be the dressing the things the same. Okay, what about C? He gave us a lot of information at C. You sure? The thing here is it's dissolved in enough water to give 100 milliliters of solution. The density, which is the mass divided by the volume, is 1.2. Do I want 115 times 2? So we're trying to find the percent weight to weight. I want weight to weight. This right here is going to help me with the weight of the solution. Right? Here, I was able to use these. You guys did it without even noticing, as 1 milliliter equals 1 gram. Because that's what distilled water is. But as I get down to this bottom one, it's not. So I've got to do the 1.20 grams per milliliter times 100 milliliters to find out the mass of the solution, which is going to be 120, right? So then I'm going to take the 15 grams divided by the 120 times by 100, and I'll get my percent. 12.5%, and it's of, it doesn't tell me what, but it is weight to weight. How do we do? Do everybody understand why I did that? Well, it says a solute. It doesn't tell me what the solute is, so I don't know weight to weight of what solute. That's what we usually say. Okay? All right, let's go on to some other. Did you have a question? Yes?
So was it just a coincidence because I had no idea what I was doing, but I tried it anyway, and I did 15 divided by 1.2, and I got the same answer?
How'd you get 122?
I said 1.2.
1.2?
Yeah.
Interesting. Shouldn't have worked, but you were lucky. Okay, all right, let's go forward. Okay, this one, we're doing volume to volume. Volume to volume. And here you have a person down on C that has 5.0 liters of blood flowing around in them that you got to deal with. Okay, so go do A and B first and then get down to C and read. And this is one that I would set up just like I did earlier. Okay, we got some answers. Yes? Anyone? Anyone? Bueller?
Well, Miss Howell, I didn't know you watched the football movie.
I just know the commercial. That's all I know. Do we have any answers? Getting bored. What do we get for A? 8%. 8.0% volume to volume alcohol. Okay, what about B? 1.11? No. What? 6%.
I said enough to be legally drunk, not alcohol.
Acetone. I hope you're not drinking acetone to be drunk. Okay. That's bad. Okay, so considering the blood volume to be this. Since it's volume over volume, as long as the volume is the same, they're going to cancel out, so I don't need to worry about it. I want to find out how much alcohol in 5.0 liters times 100 is going to give me 0.50% volume to volume, because that's going to cause a coma. So I want to know how much pure ethanol I can drink before I go to coma. When they go into the hospital, that's one of the things they test in your blood. If they think you're drunk, they want to know what your blood alcohol level is, because you might have poisoned yourself with alcohol. Okay? All right, so what do we do? What do we get for X? How much ethyl alcohol do I have, or ethanol do I have?
25 milliliters.
Good. I cannot spell alcohol, just pretend. So you had 25 milliliters. That's pure 100% ethanol. So usually alcohol is not given pure. It's usually a percent, most likely not over 50-50. Okay, so going forward. Now we're doing weight to volume. Mass to volume. We're given the solution density again. Do we need it?
Yes.
No. Why? Because we already have the volume. So it's just weight divided by volume. They gave you something extra. Be careful. Okay? You only need the density if you need the weight on the bottom. Okay, so what do we get for percent weight to volume for some solute? 14%? Okay, what about the bottom one? They gave you extra information too here. You didn't need to add anything up. Don't think molarity when you have something like that. You just need to take the grams divided by the milliliters, right? What do we get? 5%? That's just used as a label, right? Okay, any questions or problems with these? They should be pretty straightforward, right? We okay? All right, we're going to go on to talking about the lab. So everybody get your labs out. You cannot go back into lab unless you have your pre-lab done. So if you haven't got your pre-lab done, you're going to need to work like a banshee to get it done. Okay? Because you cannot do parts A or B until you have the pre-lab done. Okay? And if you don't have the pre-lab done, going back to lab is not going to help you. So you got to work your butt off. All right, so listen up, because this is important. If you want to get done before the end, listen. Everybody's eyes up here. You can help them with the lab, pre-lab in just a minute. They're not done. This is important. When you get back there, the first thing you do, one of you go fill up distilled water. Two of you go and get the distilled dialysis tubing, and you measure out 4 10-centimeter strips and cut them. Then put them in the distilled water. They have to soak for a while. They are very brittle right now. When they soak in water, they become more pliable. We can open them up. They become a tube. Okay? So you do that. You set it aside. Then each one of you, there's going to be 4 in a group, each one of you gets to make a solution up. Right now, I want you to choose who's doing what. So this will be a group, that'll be a group, that'll be a group. Okay? 2 salts, 2 sugars. Decide now. 2 salts, 2 sugars. That's part of it. You need the blue part too.
I don't think I have any of those.
So go grab it if you don't have it. I would say one of you do sugar, one of you do salt.
Oh, okay. Okay. I'll do it. Yeah. Wait, but don't we have to, measure, a bar?
We're going to talk about each one. Just decide what you're doing. Everybody got a decision on what you're doing? One of you guys are doing salt, one of you doing sugar. So decide between the two of you.
Salt, so sugar.
Okay, listening up here now. You know what you're doing. Only pay attention to the part that I am that you're going to do. So if you're doing salt, you're listening to me right now. Salt, you're going to weigh, you're going to measure out half distilled water in your 250 milliliter volumetric flask. You're going to go weigh what you figured out your salt you needed to weigh in your pre-lab. You're going to pour the salt in here. Now, you're going to take and crunch that end so it becomes a V so it goes in easier. Okay? You're going to put it in here. You're going to swirl, 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 get it dissolved. You're going to fill it up to 250. Then you're going to pour it into a cuvette. 1 time, dump it out. 2 times, dump it out. 3 times, bring it to me. I'm going to put it into a colorimeter. I'm going to read, see how close you really were to what you should have got. I'm going to tell you what you should have got. I'm going to tell you what you got. You're going to write those down on your paper somewhere because you're going to tell me the percent off you are from what you should have been. Okay? Yes. Yes.
So, repeat everything you just said.
Okay.
Put it up as a little triangle, you put it in.
You fill up in a little triangle.
What? No, like the little strip or whatever. What are you talking about? Okay.
250 milliliter volumetric flask. Full. Half full.
Yeah.
Weigh out what you figured out your salt was
Yeah.
in your pre-lab. Pour the salt into that water. Swirl, swirl, swirl till dissolved. Fill it up to the line.
Why'd you say try these?
Then you're going to take the cuvette, pour a sample in, dump it out. Pour it in, dump it out, pour it in, keep it, come bring it to me. I'm going to put it in a colorimeter to get the measurement. You're going to write down your measurement and the true measurement. Give me a percent error.
How much are we putting in the cuvette?
You're going to fill it about 3/4 full.
And that's just our estimate.
Yes. Okay? All right, sugar, listen to me because you're different. Okay, sugar. You're going to weigh out what you figured out in the pre-lab. You're going to weigh a styrofoam cup. You're going to fill the volumetric flask up to 250 with distilled water. You're going to pour that 250 milliliters into the cup. You're going to weigh the cup again. You're going to then pour your sample into the cup, stir, stir, stir with a stirring rod until it is all mixed together. Once it's all mixed together, you're going to grab a cuvette, pour in once, dump out. Pour in twice, dump out. Pour in third time, bring it to me. Do not throw these away. You need both of these in part C. Okay? You need 2 of each. Yes.
We're doing 2 of
One person is doing one of these, but by the time your group of 4 gets done, you'll have 250 milliliters of each. Yes. Just in the sink. Just in the sink. Yeah, you're just rinsing out with this solution so it doesn't have anything else in it. Okay, now, stop. Look at me. That's part A and part B. Now I'm going to go through part C because you have to use what you made in A and B to do C. Okay? This is where we go back to your dialysis tubing. You're going to pick the dialysis tubing up out of the water and you have to sort of rub it like this to get it to open. Okay? If your fingers are wet, it opens easier. So if you have to dip your fingers in the water and rub it till it opens. We have found it easier to use the string in the back. So you're going to take string, you're going to tie off one end. Make sure you use a square knot, not a granny knot, because a granny knot will come out. Okay? Tie one end off. On the second, then you're going to fill it up with 5 milliliters of solution. You're going to do 1 that's your salt solution, 1 that's your sugar solution, 2 that are your distilled water. It works better if you work in pairs, in teams, because somebody's going to have to hold it while the other person's trying to hold it open while the other person's pouring it. And it's a lot easier to have somebody tie it when somebody else is holding it. Right? So once you get it full, you're going to tie the other end. And again, I would use the string. I found it to be a lot easier. If you're great with elastics, I've got elastics back there. Once you got it tied with a string, I've got 2 colors back there, and only 2 colors. Sorry, I should have got the one that was multicolored. There are elastic bands. You can put one color of elastic band on the end of that so you can know what one it is next time, because it might not still be the same color. Does that make sense? Okay? So you're going to have to put in your notes what color rubber band you put it on a certain one. You're going to dry it off. So once you get this way, you put an elastic band right here. Maybe I wanted a red elastic band. I put it right there just so I knew which one it was. I'm going to dry it off with paper towels. I'm going to weigh it. Then I'm going to set up beakers just like this. I'm going to put this on a piece of paper, on a tape, onto beakers. So I have 5 beakers.
So the white ones up there are distilled water?
Right. Okay, so I'm going to put that on each beaker. I'm going to put a label on each beaker. And I also need a team named on each beaker. So nobody takes our stuff. Okay? So distilled water in the red, distilled water in the blue. The blue in distilled water, the red in distilled water. Then you're going to weigh a prune and put it in distilled water for E. Okay, the prunes are pretty old and crunchy, so they don't have much weight to them. Label all of them, and then you're going to put them where I show you. You'll see the other beakers laid out from other periods. When everybody gets theirs done, I'll cover it with cellophane so it doesn't evaporate. Any excess red and blue solution can go down the sink. Rinse everything out, cuvettes rinsed out, and back to me, and then you're back here. Questions? We got to move fast. We got just over 35 minutes. Okay? You have to have your pre-lab stamp before you go back. So if you got it done, come get your pre-lab stamp. If not, stay in here until you get it done. Come. Fast as you can.
Right, but it's done.
Let's get the sugar. Give me the
Yes,
stuff.
you're good. Go.
Go.
Okay, go.
Thank you.
Okay, whoops, wrong place. Go. Okay, go. Okay, we're off. So this, pencil. This is not 0.5, it should be 2.5. 0.25, because we're putting it in 250 milliliters of water. So here, this should be 0.625 and 0.06. You're right, so tiny, I don't know how to do it. 0.0625 times that. So that's going to be different. That's going to be different. Again, same thing here. This should be 0.25. And so that's going to end up different here. 0.25. Get that. And that answer goes right here. And that'll give you a different answer here and here. Okay, so go quickly recheck that. Okay, I got your number. Oh, that is just
Did it actually stated in here?
these two, because they're both dissolved in
bottom.
water.
Oh, okay.
So you put that
And
on
then
real
this
quick.
one, I did this one in 250 milliliters, but I just used
This one's
the,
not right.
Yeah,
This one's
because I
right.
only did the 100.
Okay, so
So
just
it
really
had to
quick
be
fix it. Yep, it needs to be 250. Guys, the numbers need to be on 250, not 100. 250 milliliters. So this right here is going to be 250, and this is in 250 milliliters. So this 250 milliliters will become 250 grams and will become 0.25 kilograms. Sorry, going off the side there. Okay, and I'm going to just rearrange this real fast because I've had lots of kids have problems. So moles divided by liters. We're solving for moles. Moles. Is equal to molarity times liters. Down here you've got molality, which is a funky looking M, and you get moles divided by kilograms. And so you get moles here is equal to the molality times kilograms. And then once you get moles, you're going to change it using these numbers down here to grams. Okay? So you just do a regular T table. And you'd put 1 mole on the bottom and that mass on the top. And you put this answer right here, right there.
Oh, okay.
Okay?
Is this right for this first one?
Yes.
And
Much
then
better.
is that right for this?
Yes. Okay, as soon as you get it, let's stamp it and head back. You're going to have to hustle butt.
One second, I have a question. I'm confused on these two steps.
Okay, so this one is molarity, which is moles per liter. So you're going to take moles is equal to molarity times liters. We're going to use, this needs to be 0.25 because it has to be in liters. 250 was the milliliters.
Okay.
So 0.25 times that, and you got that. That's right. So down here, molality is equal to moles divided by kilograms. So you get mole is equal to molality times kilograms. Again, 250 milliliters is equal to 0.25 kilograms because it's a 1-to-1. And then you just plug in, and then you'll use the 342.297 in 1 mole gram, and you'll put this answer down there.
So, this answer down here? Or?
No, so you're going to take this, which is 0.25 molality times 0.25 kilograms, and that's going to go
The
there.
label like grams?
Okay, so you're good to go, go. You're good to go, go. You're good to go, go.
Pressure of
You got,
backside?
yep, you got these 2 more questions. 3 more questions.
This one, it's just the masses, like the bottom number on each of those added up.
Colligative properties.
Freezing point depression, boiling point elevation, osmosis is possible, vapor pressure lowering. What? 21 points, yep.
That goes here.
Luke, are you coming?
So freezing point, boiling point?
What? Work.
I am working.
Oh, okay.
It's just faster to just say straight up where's the more mass salt.
Okay.
Vapor pressure.
Vapor pressure lowering, boiling point elevation, freezing point depression, and osmosis is possible.
How do you spell osmosis? Freezing point, boiling point, vapor pressure.
Lowering, freezing point lowering, boiling point elevation, so boiling point up, vapor pressure lowering, and osmosis is possible.
What correlative property? That's the.
So we're going to explore all of them except for vapor pressure.
Literal values.
So that you're going to get from right here. These 2 are what go here and here and here and here because we're using water.
This part.
So this part right here is molarity is equal to moles divided by liters. We're looking for moles.
Okay.
So moles is molarity times liters. We're using 250 milliliters, which becomes 0.25 liters.
Okay.
So once you get that answer, you're going to put it in, get the answer here,
Okay.
and then you're going to go 1 mole on the bottom, and this is not the right mass. This should be 58.44
1.86.
grams.
Is it 1.86 for both of them?
58.44
Because we're only
grams.
using water.
Yeah.
Yeah. Okay. So it's just.
So, and then you'll get your answer
1.86,
here.
1.86.
This one right.
So moles times liter. So the
So you'll have 0.25 molarity times 0.25 liters, and that answer will go here.
So just 0.25 plus 0.25. We go to
Molarity. This is wrong. That should be that. So talk to him and figure it out.
Okay. And
Okay.
does anything go there?
No.
Okay.
And then this one is moles divided by liters. So mole
And that's the number I get out of that.
is equal to,
Sorry. Hold on. Thanks.
okay, and then moles equal here to molality times, whoops, this should be kilograms, times kilograms. And again, we're using 250 grams of water, which is 0.25 kilograms.
Okay.
So we're going to times those 2 together. Again, you'll get the same 0.0625 moles. This time, you're going to put that there, and then on the bottom 1 mole, and on the top 346.3. So I just put like that and get my answer.
Okay. Thank you so much. Still
And
trying
I'm
to.
gonna. Did you get the other page done? Yeah, you just need to copy that down in all of them but vapor pressure is what we're
but
doing.
vapor.
Yep, I'll stamp you to go real quick. Yep, that's it.